Hello class, welcome to this video on AP Stats, Chapter 7. So we're going to look at version or assessment A. So for the first question, we have a six-sided die with sides numbered 1 through 6 will be rolled a total of 15 times. Let x bar 1 represent the average of the first 10 rolls, and let x bar 2 represent the average of the remaining 5 rolls. What is the mean, mu x bar 1 minus x bar 2 of the sampling distribution of the difference in sample means? X bar 1 minus x bar 2. Okay, so first off, let's write down the formula. So we got, we know from the formula sheet, if we use the formula sheet here, we have mu x bar 1 minus x bar 2 is equal to mu x bar 1 minus mu x bar 2. So we can just subtract the two means. But we know that the mean of the sampling distribution of x bar, we know that in general, that the mean of the sampling distribution of sample means is equal to the mean, right? So we're just going to call it the mean, or the mean of x, okay? We'll just call it mu x, all right? So in this case, we just have mu x1 minus mu x2, just regular x instead of x bar. However, we're looking at the same fair six-sided die. Okay, so really, if you think about it, you're just looking at the same die. And remember that the average to find the average of a die, remember the formula for finding the expected value of a discrete probability distribution is given by the sum of x times p of x, right? And since in a die, right, if you were to do the probability distribution of a die, you have x, p of x. Well, that's just going to be, let me do, so this is x, and then this is p of x equals little x. You have 1, 2, 3, 4, 5, 6, but they're all equal to 1 out of 6, right? So essentially, you just have 1 out of 6 times 1 plus 1 out of 6 times 2, dot, 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 right? And you can just pull out the 1 out of 6 and you have 1 plus 2 plus 3 plus 4 plus 5 plus 6. All right, so essentially, you're just adding them all up and then divided by 6. Well, then that gives you 3.5, okay? So it's just the basic average of all of those numbers, right? So you just, and then divide by 6. Okay, so just add them up, divide by 6. And so that's your expected value, right, of the die. But since it's the same die, this is really just mu x minus mu x. There's no reason to distinguish between 1 and 2 because they have the same result. It doesn't matter how many times you roll it, right? It's still going to be the same expected value, right? According to this distribution. And so really you just get 3.5 minus 3.5, which is 0. Okay, so hopefully that made sense. So we're just looking at B for the answer. Okay, so let's look at number 2. According to government data, the 22% of children in the United States under the age of 6 years live in households with incomes that are classified at a particular income level. A simple random sample of 300 children in the United States under the age of 6 years was selected for a study of learning in early childhood. If the government data are correct, which of the following best approximates the probability that at least 27% of the children in the sample live in households that are classified at the particular income level? Okay, so it looks like they give you the 22%, so that's sort of like my P, so we could assume that's the true value based on the government data. And then a simple random sample of 300 children in the United States under the age of 6 years. So we got our sample size of, so that's my N. And then it says, which would follow best approximates the probability that at least 27% in the sample. So that means that's your P hat, okay? All right, so when you go to your AP formula sheet, let's see if I can go to it. So let's go to the AP formula sheet. So here we got the standardized test statistics. So they don't technically tell you what the Z is directly, but they tell you what it is here indirectly, okay? The standardized test statistic. So the standardized test statistic can be Z, or it could be any other test statistic that's standardized. Z is the standard, the standardized Z-score, right? So statistic minus parameter divided by standard error. Okay, so in that case, okay, Z is statistic. This is the value. In this case, the statistic that we're looking for is p hat, right? The parameter, that's p. Okay, and then the standard error. Okay, so what's the standard error? Well, the standard error for the test statistic, if you go here, that's basically the standard deviation, but of the distribution. So basically, so the standard deviation for p hat. All right, so that's this right here. But you could, if you don't have, sorry, not this one, the standard deviation, right? Standard deviation. So when they say standard error, you basically you can use this to approximate this, right? However, if you already have P, which we know we have P, then we would use this formula, okay? We wouldn't use P hat if we already know what P is, okay? So since we know what P is, instead of using like the regular standard deviation of the sample statistic, we're going to use the parameter sigma, okay? So we're going to be using that, P times 1 minus P over N. Okay, so let's go back to this. So then this is going to be sigma P hat. Okay, so I just wanted to show you that this is where you can kind of get a structure of the formula for Z if you don't remember. Okay, but again, it's better to just kind of know what it is so you don't have to worry about trying to interpret the table, right? So again, let's just kind of write down the value. The Z is value minus, in this case, so the statistic, which is like value minus parameter divided by, yeah, so this is what I usually say, right? This is what I usually tell you guys. I usually tell you value minus mean divided by standard deviation, right? That's usually what I tell you guys. So in this case, the value, what's the value? P hat. What's the mean? The mean is the mu of P hat. But what's the mean of P hat? Okay, well, if you go here, the mean of P hat is right over here. The mean of P hat is just P, right? And so then we're going to use that. Okay, so I'm just trying to teach you how to interpret the table, say, and based on what we talked about in class. All right, divided by the standard deviation of P hat, right? Okay, so we got P hat minus P, because now we know that mu P hat is just P, divided by the standard deviation, which is the square root of P times 1 minus P divided by N. Again, super duper important. If you know what P is, then you're going to use P here. If you do not know what P is, like for example in confidence intervals, you're going to be using the standard error here, right? So you just have to be super duper careful when it comes to these kind of things. Since you know P, you use P. All right, so in this case, we got P hat, so we want it to be at least, so that means greater than. Okay, so we're going to say Z is greater than P hat. Well, let's just write down the formula now that we have the formula. So P hat, we said was 27%, so 0.27 minus P is 0.22 divided by square root, and then this is where you don't, yeah, this is where you would use the P and not the P hat. Because if you use P hat here, you would choose, if you use P hat, you would end up choosing C, right? Because C has P hat. Notice that right there is P hat times 1 minus P hat divided by n. Okay, so here they use p times 1 minus p divided by n. Okay, so see the difference there? So you want to be very careful here. So p 0.22, 1 minus 0.22 divided by n, and n was 300. So here you're looking at B as the answer. Okay, super. I can't emphasize that enough. You just got to be careful with things like that. All right. So number 3. A manufacturer of cell phone batteries claims that the average number of recharge cycles for its batteries is 400. A consumer group will obtain a random sample of 100 of the manufacturer's batteries and will calculate the mean number of recharge cycles. Which of the following statements is justified by the central limit theorem? Okay, so remember the central limit theorem, what that says is that the central limit theorem says it doesn't matter the shape of your distribution, the original distribution, right? If you take a large enough sample, n is greater than or equal to 30, right? Then your sampling distribution of sample means, so that's your x bar, is going to approximate a normal distribution where the mean of that sampling distribution is going to be approximately equal to the mean of the original, and the standard deviation is going to be smaller than the standard deviation of the original because it's going to follow this formula. Okay. All right. So in that case, the answer is D. The distribution of the sample means is approximately normal because the sample size is greater than 30. Okay. So that's got to be the answer. Remember, it's not the number of recharge cycles. It's the sample mean of the number of recharge cycles. Okay. So you got to be careful with that. All right. So that's number 3. Number 4, an international polling agency estimates that 36% of adults from country X, okay, were first married between the ages of 18 and 32, and 26% of adults from country Y were first married between the ages of 18 and 32. Based on the estimates, which of the following is closest to the probability that the difference in proportions between a random sample of 60 adults, so that's my N1, and we'll call this P1, and then we got P2, all right? From country X and a random sample of 50 adults from country Y, so that's N2. Country X minus country Y is what they want us to do. So that's P1 minus, or yeah, let's call it PX and PY, just to make it easy, okay? And I'll call this NX and I'll call this NY, just so that we don't confuse it. We know that X is country X and Y is country Y. Who were first married between the ages of 18 and 32 is greater than 0.15. Okay, so we want the which of the following is closest to the probability. So we want the probability that the difference px minus py is greater than 0.15. That's what they want at the end of the day. Okay. Okay, well now first off, we can assume that nx and ny, so nx and ny, are both less than 10% of their respective populations. Okay, so I'm going to say less than 10% of population X, and ny is less than 10% of population Y. Remember, that tells you that if it's less than 10%, then that means you can use the standard deviation formula. Okay, which is the standard deviation px minus py. So you can use that formula, which is what we're going to do here. And then we can also approximate this with a normal distribution by satisfying, so let me write this is the 10% condition, and then we can satisfy the large counts condition, right? So this means that it's going to be approximately a normal distribution. So that's going to be nx px, and that has to be greater than or equal to 10. And then nx times 1 minus px is greater than or equal to 10. And then ny py greater than or equal to 10. ny 1 minus py greater than or equal to 10. So in that case, if you did, for example, 36% was px, so 36% of 60, right? So we can, let's just verify this, because this is good to do in the free response anyways. This is not something that you would necessarily do in the multiple choice, because you would assume that you can use a normal distribution. You can quickly test it, of course, but when you see this type of problem, they're assuming you could just use normal distribution and then use the formula. But we want to make sure that you know how to do this, for example, in a free response to test the conditions. All right, so nx and px. So we get 0.36, and then we had 60 people, I believe. 0.36. All right, so that's definitely greater than or equal to 10, and then 60 times 1 minus that is definitely greater than or equal to 10. All right, and then 50 times the other one was, I forget what py was. Py is 0.26. This is greater than or equal to 10, and then 50 times 1 minus is definitely greater than or equal to 10. So that means it's normal, okay, approximately normal, with a standard deviation of mu and sigma. It's approximately normal. Let me just write that. All right, so that means we can calculate this. So let me just do it over here. All right, so let's calculate the z-score, or let's calculate the mean. So we know that the mean of mu px minus py is just going to be px minus py. That's from your formula sheet, okay? And then we know that the standard deviation of px minus py, so let's look that one up. So standard deviation right over here of the difference in two proportions. So for two populations right here, p1 minus p2, we have this formula, okay? p1, 1 minus p1 over n1, right? And we're gonna use that formula there. Okay, let's go back. We got square root px times 1 minus px over nx plus py times 1 minus py over ny. All right, and then so we can just calculate that, and then we can use a normal CDF. Okay, so normal CDF. So let's just calculate this real quick. So px minus py, we have px was 0.36 and py was 0.26. So you subtract those to get 0.10. All right, and then we double check that that's the case. Yep. All right, and then let's calculate this. Square root 0.36, 1 minus 0.36 divided by, we had 60 people. And this one was 0.26 times 1 minus 0.26 divided by 50 people. See what we get for that. Okay, we get about 0.088. Okay, so now we can use the normal CDF, right? So we're going to say normal CDF of those two numbers. Okay. Normal CDF, the lower. Okay, so the lower here, and remember we're doing greater than 0.15. So that means that if you were to do your graph, you have 0.15 here, and we want to do greater than that. So your lower has to be 0.15, and your upper has to be infinity, which would just write 10 to the 9th power or something like that. And then your mean equal to 0.10, and then your standard deviation is equal to 0.088. Okay, and I do this and I get about 0.285, all right? And then the closest answer is B. All right, so it's a lot going on, and I just like to take time on it just to make sure that you understand every single facet of the problem. All right, so number 5, a recent study was conducted to investigate the duration of time required to complete a certain manual dexterity task. The reported mean was 10.2 seconds with a standard deviation of 16 seconds. Suppose the reported values of the true mean and standard deviation of the population. Okay, so suppose that those are the true values, so mean, standard deviation. If a random sample of 144 subjects is selected from the population, what is the approximate probability that the mean of the sample will be more than 11 seconds? So the probability that the mean is greater than 11. So this is a central limit theorem problem because we're looking at the mean of the sample of the sample is greater than. So again, so this is, remember that central limit theorem states that we're going to have a normal distribution with a mean of mu and then a standard deviation of sigma over square root of n. Okay, so that's going to be what we're going to do. So we know that the mu x bar is just mu, which is 10.2. Okay, that's in your formula sheet. And then we know that the sigma x bar is sigma divided by square root of n, and which is sigma is 16 divided by square root of 144 people. Square root of 144 is 12. So this is 16 over 12. All right. Okay, so this reduces to 4/3. Okay. All right, so we know that the standard deviation x bar is 4/3, and we can use normal CDF here now. Okay, so normal CDF. And then remember, more than 11 seconds. So if this is 11 and you want greater than, then 11 is the lower value. All right, and then upper is 10 to the 9th power, and then we got the mu. The mean is 10.2. The standard deviation is 4/3. We get our answer. All right, and if you do that, you get the answer B. All right, so number 6, a recent survey concluded that the proportion of American teens who have a cell phone is 0.27. The true population proportion of American teens who have a cell phone is 0.29. Okay, so I said the true value, so that's my P, and then I say a recent survey concluded that the proportion is 0.27. All right. All right, it says for samples of size 1,000 that are selected at random from this population, what are the mean and standard deviation respectively for the sampling distribution? So, okay, so for the sampling distribution, the sample proportion. So they got a proportion of p hat. So that's a specific value that they got, that they concluded based on their data. But the true value is 0.29. So we're going to focus on the true value because we know that the mean of the p hat is going to be equal to p anyways. So that's from the formula. So the mu of p hat is 0.29. The standard deviation is just the formula that they give you, which is p times 1 minus p divided by n. All right, which is in this case the 0.29, 1 minus 0.29 divided by 1,000. Okay, so here the answer is D. All right, so number 7, a simulation was conducted using 10 fair 6-sided dice where the faces number 1 through 6. All 10 dice were rolled and the average of the 10 numbers appearing face up was recorded. The process was repeated 20 times. Which of the following best describes the distribution being simulated? Okay, so the process is repeated 10 dice were rolled, average of 10 numbers. The process was repeated 20 times, which is following best describes the distribution being simulated. Okay, so first off, we want to find the average of the 10 numbers, which means that eliminates these two because those deal with proportions, and we don't want that. We want the sample mean, okay? So remember that this is a sampling distribution where we're dealing with x bar. We're doing the average of the 10 numbers, right? And so, and we have n is equal to 10. When it says the process is repeated 20 times, do not confuse that as the n. Okay, so what that's saying is you're taking 10 dice, so n is equal to 10. And once you roll the 10 dice, you get a number from that, which is the average of the 10 numbers. Okay, and you're just doing this 20 times. So the 20 is the number of trials. 20 is not the sample size, okay? So the sample size is 10 fair 6-sided dice. So be careful with that because you're going to then assume it's n equals 20, and that's incorrect. So it can't be that. So it's either A or B. So the mean of a sampling distribution, excuse me. So the mean of this sampling distribution is equal to the mean of the original distribution, which is just x. Okay. So what is the mean of x? Well, the mean of x is just the mean of a die, right? So the average for the numbers on a die. So what's the average of the numbers on a die? Well, we did that earlier in the previous question, but remember we calculated by doing this, right? Which was 1, 6 times 1 plus 2 all the way to 6, right? So we did that earlier, so go back to that previous question, and we got 3.5, okay? So it has to be 3.5, so far both of these have that. And then we remember that the standard deviation of the sampling distribution is approximately the standard deviation divided by the square root of n, okay? And I say approximately, the reason why I say approximately is because we have to satisfy the 10% condition for that, you know, or you know, those conditions or whatever. But we're just gonna say that it's equal, approximately. We're just gonna round it anyway. So, and then the standard deviation. Yeah, let me just put equals there, because in the formula sheet we have equals. So this is the parameter of the sampling distribution. It's going to be equal, but we're just going to approximate it because it's going to be a decimal anyways. So it's got to be one of those two. So how do we calculate this? So we're going to call this sigma x. So how do we calculate sigma x? Well, remember sigma x, the formula for that, and this is in your formula sheet, is the square root of the sum of x minus mu squared, x minus mu x squared, times the probability. All right, so that's what it is for a die. Now you could do this on the calculator. Type in on the calculator 1 through 6, right? Let me see if I can find it. So on the calculator, you're going to type in 1 through 6, right? And then you're going to type in the probability is 1, 6, 1, 6, 1, 6. And then you can get the mu and the standard deviation using 1var stats, okay? So we can show you that in a second, just to make sure you know how to do this. But, you know, you just calculate this formula, and I'll show you the first few calculations. So square root of 1, you can get 1 on a die, minus, remember the mean was 3.5, squared times 1 out of 6, plus dot dot dot, and just end with the number 6, minus 3.5 squared times 1 out of 6. Okay, so let's show you how to do this on the calculator. All right, so then we go to stat, we go to edit, let's delete all these numbers. All right, and we got, okay, so we got 1 to 6. All right, and then we type in 1 out of 6 for all of these. So 1 out of 6, so on and so forth, okay? All right, so we got 1 out of 6 for all of these, and then you're gonna go to stat, and then go to calculate, and then one variable stats. Okay, and then remember, we're gonna select list 1, and then we don't care about doing list 2, so I'm gonna delete that. So we just want list 1. All right. Again, if you don't have this menu, you would hit second stat and then select list 1. Okay. Oops, let me go back to that. One variable stat, and then go to calculate. Oh, actually, technically you would do list 2, so let me actually do list 2 here. It doesn't matter in this case because the probability is 1 out of 6 for all of them, but if the probability changes, 1 out of 6, 2 out of 3, whatever, if the probabilities change in this list right here, let's go back to this list. If the probabilities change here, then you're going to want to include list 2. So let me just do that just to be on the safe side for any situation, and then we'll put list 2 here. So second stat, and then we'll do list 2. Again, in this situation, doesn't matter because the probabilities are the same. All right. So you go. So you get x bar is 3.5, and then you get the sigma x is 1.708. Okay, that's what you get. All right. So if you calculate this, you get 1.708, like we said. But remember, that's not the answer because that's just sigma x. And then so we can calculate this. We can just say, okay, 1.708 divided by the square root of 10 dice, right? And then if you do that, you get 0.5. 0.054, around there, approximately. So the answer is A. All right, so next question. Based on records kept at a gas station, the distribution of gallons of gas purchased by customers is skewed to the right. All right, so it says skewed to the right with a mean of 10 gallons. So that's your mean, and then standard deviation of 4 gallons. Okay, a random sample, so that's N is 64 customers are selected, and the sample mean was recorded. Suppose the process of repeating a random sample of 64 receipts and recording a sample mean was repeated for a total of 100 samples. Okay, now be careful. The 100 samples is not the N. The 100 samples is just 100 times that you do the sample, 100 different trials, okay? So the sample size is N, 64. And notice that that's greater than or equal to 30, right? So that means it has to satisfy, by the central limit theorem, the has to be normal, right? Approximately normal. So even if it is skewed to the right, it's still going to be, the X bar is still going to be approximately normal if you were to do the sample mean, okay? Not the X, the sample mean, which is X bar. So in this example, we can eliminate A, B, C from the answers because that's saying it's skewed to the right, which is not correct because we're talking about the sample means, right? By the central limit theorem, must be normal, and then the mean of X bar is going to be the same thing as the original mean, which is in this case was 10. The standard deviation, remember, is going to be the original standard deviation divided by the square root of N. So it's 4 divided by the square root of, in this case, 64. Okay, don't use 100 there. Do not use 100 there. Square root of 64. So we have 4/8, which is 2. Well, it's a half, right? So it's a half. I was going to say 2/4, but it's a half. So the answer is D. Now notice that if I did use square root of 100, I would get a standard deviation of 0.4, which is not correct. Okay, this is not correct. So be careful. All right, number 9. A manufacturer of cell phones screens has found that 5% of all screens have defects. Let PD represent the population proportion of all cell phone screens with a screen defect. Therefore, PD is 0.05. For the sampling distribution of the sample proportion of cell phones from this manufacturer with a screen defect for sample size 400, mu P hat D is 0.05. Which of the following is the best interpretation? Okay, so we just want to interpret that, okay, at the end of the day. All right, so let's look at A. For a randomly selected cell phone screen from this population, the mean number of screen defects for the selected screen will be equal to 0.05. No, that's incorrect. Remember, it's not for a randomly selected cell phone. In this case, what we're talking about is the mean of all sample proportions of cell phones, right? For every sample of size 400 from this population, the proportion of screens with a defect will be 0.05. No. The proportion will not be 0.05. The proportion is going to change because every sample yields a different result, right? But then the average of those different samples will be 0.05. So it's not B. For all sample size of size 400, the mean number of defects is 0.05. No, not the mean number, and so not the mean number of screen defects. It's the proportion of cell phone screens. The average of that, okay? So the average of the proportion of cell phone screens, okay? So not C, just be careful with this, right? With this type of question, because we're doing the mu of P hat, okay? So that means we're doing the average of the proportions, right? For all sample size of 400 from this population, the mean of all resulting sample proportions of cell phone screens with a screen defect is 0.05. That's what we're looking for. The mean of all proportions, sample proportions. In other words, mu of P hat, right? With a screen defect. So this is the answer. All right, so number 10, consider a population consisting of 4 children with ages in years 2, 5, 6, and 11. The population mean age is 6 years, and the population variance is 10.5 square years. This is the population variance, so be careful there, okay? So we got the mean is 6. The population variance is 10.5. Okay, so then let's find the standard deviation to see what that is. It's the square root of 10.5. Well, let's see what that is first off. So we got square root of 10.5. So we get 3.24. All right, so let's write that out. 3.24. So that's the standard deviation. Okay, so we got mean and standard deviation of the population, and then we got our sample, which consists of these. For simple random sample sizes, sample random samples of size 2 taken with replacement, what are the mean and standard deviation of the sampling distribution of the MAGE? Okay, so then this is size 2, so n is equal to 2. So we know that if we continue to do, like, for example, if we continue to do all the possibilities of these 4 children, right, 2 and 6, 2 and 5, 2 and 11, whatever, and we take the x bars of all of them, and we find the mean, well, then the mean of x bar is just going to be the mean, which in this case is 6. And then the standard deviation of this is going to be the standard deviation of the original divided by the square root of n. In this case, n is 2. But we know that sigma is 3.24, so that's going to be divided by square root of 2. So let's see what that is. 3.24 divided by square root of 2. We got 2.29. And then the mean is, we said the mean was 6. Okay, so the answer is D. All right, so number 11, a large manufacturing company has tens of thousands of employees, and 30% of the employees have completed a management training course. Suppose a simple random sample of 50 employees is selected. Which of the following is closest to the probability that more than half of the sample will be employees who have completed the management training course? Okay, so here it says, so first off, we got 30% of the employees, so that's P, okay, 0.30. Sample of 50, so n is 50. And it says the probability that more than half of the sample, okay, so more than half of the sample, so that means p hat is greater than 0.5. That's what they're saying. They're saying the probability that p hat is greater than 0.50. So what's the probability that more than half, right? More than 0.50. So p hat is 0.50, and then we want to be greater than that, right? And so when we calculate this, we can say, okay, so first off, we know that it's a large manufacturing company, and so that means that it satisfies the 10% condition. So that means that the sample of 50 people is likely to be less than 10% of the population, right? Because so that means we can use sigma p hat, okay, which is the square root of p times 1 minus p divided by n. Okay, so we can use that formula. And it satisfies the large counts condition, n times p, so 50 times 0.30 is greater than or equal to 10. That's true. And then 50 times 1 minus, so if I do this, I get 15, which is greater than 10. And if I do 1 minus, then I would get 35, which is greater than or equal to 10. Okay? So that means it's normal. Approximately normal. Which means that I can use the normal distribution, and so I can use normal CDF. Remember that the mean p hat is equal to p. So in this case, the mean is 0.30, and then we need to calculate the sigma p hat. So let's do that here. Square root 0.30 times 1 minus 0.30 divided by 50 employees. So we calculate that. Let's do that real quick. So we got square root 0.3 times 0.7 divided by 50. So 0.0648. So 0.0648, and we're going to use the normal CDF. We want it to be greater than, so that means if this is 0.50, we want it to be greater than that. So that means the lower is 0.50. The upper is infinity, or 10 to the 9th. And then the mean is 0.30, and the standard deviation is 0.0648, what we just calculated there. All right. Okay, and so when you do this, you get 0.0010. So it looks like it's going to be A here. Okay, so the answer is A. All right, so number 12, a fair die has its faces numbered from 1 to 6. Let random variable f represent the number landing face up when the die is tossed. Okay, and then the probability distribution for the random variable has a mean of 3.5 and a standard deviation of 1.7078. Oh, look at that. So if you looked at this question, you could have used that for the other stuff. But we showed you how to get that, 3.5 and then 1.7078 on the calculator, right? So that's what they're saying there. Consider simulation with 400 trials designed to estimate the sampling distribution of the sample mean for 5 tosses of the die. For each trial, the die is tossed 5 times, and the mean of the 5 values landing face up is recorded. The mean and standard deviation of the results of the simulation should be close to which of the following? All right, so remember, this is one of those ones that they try to trick you. They say the simulation is 400 trials. That is not my n, okay? Remember, 400 trials just means that you're doing whatever trial 400 times, right? Whatever process you're doing, you're repeating it 400 times. That's not the sample size. That's the number of samples, okay? The sample size, it says for each trial, the die is tossed 5 times. That is your sample size, okay? Because you're collecting a sample of 5 numbers, and from those 5 numbers, then you're finding the mean of them. And then you're repeating this 400 times, right? So that's your sample size. This is what messes up students all the time. So we want to be careful with that. So we know that the mean is going to be the mean of the original, which is 3.5. The standard deviation is going to be your standard deviation divided by square root of n. And so we get 1.7078 divided by the square root of 5, okay, which is 0.76-ish, right? So the answer is B. Now, if you tried to do square root of 400, you may end up getting this answer. I'm not sure, but there's a good chance you would get that answer and you would get it incorrect. So be very careful with that. All right. Number 13, a certain statistic will be used as an unbiased estimator of a parameter. Let J represent the sampling distribution of the estimator for samples of size 400. That's the sample size, so that's your n is 40. Let K represent the sampling distribution of the estimator for samples of size 100. So that's another sample size there. Which of the following must be true about J and K? Okay, the expected value of J, that's the mean, will be equal to the expected value of K. Yeah, that's true. We know that that the expected value for both should be the same. Because the sample size, because you're taking the sampling distribution of the estimator, right? So that makes sense. So the sampling, the expected values will be the same. However, the standard deviations will not be the same, right? So sigma j does not equal to sigma k, because remember that the sigma j is going to be sigma over square root of nj. And nj is 40 and nk is 100, right? Okay, so we just got to be careful with that. It's not going to be the same for that. The variability will be equal, so no. The expected value will be greater, no. The expected value will be greater, no. Expected values will be equal, yes. The variability will equal, no. Expected values will be equal, yes. The variability for J will be greater than the variability. Okay, so let's see if that's true. Well, because this here is, so square root of, what was it, 40? Yeah, 40, and the other one was 100. So in this case, if we look at, oops, sorry about that. Sorry about that. Okay, so we got square root of 40, and we want to compare this to square root of 100. Well, then this one's going to be bigger because smaller denominator means bigger variability. So this variability for J would be greater. So that is true. Okay, all right, so then it has to be E. The variability is greater for J than K. A machine is used to fill bags with a popular brand of trail mix. The machine is calibrated so the distribution of the weights of the bags the trail mix is normal. Okay, so we got normal with a mean of 240 and standard deviation of 3. Of the following, which is the least weight of a bag in the top 5%? So that means, and you're just doing the least weight. So you're not doing X bar, right? You're just doing X, okay? So we want to figure out what X is. X is question mark. The top 5%. So we got the top 5%. So that means this is that means the top 5% means the area to the right is 0.0500. So if you were to look this up, you can look this up, and we can look this up with a table so we can kind of show you. And then we can also do the calculator, obviously. But if we go to the table, we look at the value that is closest to 0.05. Right here. So which value is closest to 0.0500? Oh, actually, let's go back, because this table gives you the area to the left, right? So let's take that into account. So if it's giving you the area to the left, then that means that the area to the right is 1 minus, which is 0.9500. So we're going to look that up in the table, 0.9500. Okay, so let's go back to the table. All right, so we need an area of 0.9500. Okay, that looks like either one of these, right? So then the z-score is about 1.64. Okay, so that's going to give you my z-score. All right, so now we got our z-score, which is about 1.64-ish. Let's go back and show you how to calculate the x, okay? So now we got z is about 1.64. So the formula for, remember that z is x minus mu divided by standard deviation. So if I solve for x, using some algebra, of course, we would get mu plus z sigma. And now we know that the mean is 240. We know that z is, we just calculated it, 1.64. And we know that sigma is 3. And so we can use that to calculate the x value. All right, but let's show you with the calculator. So the calculator, we use inverse norm. So inverse norm, and then we provide the area. Now the area has to be to the left, okay? So we have to do 0.9500, or it's gonna give us the wrong z-score. It's actually gonna give us the negative version if we use 0.0500, okay? And then the value here, what's the area is 0.9500, then we need the mean. The mean is 0 and the standard deviation is 1, guys, because you're doing z-scores. If you're doing I'm sorry, you don't have to do the mean and 0 and standard deviation 1. If you want a z-score, then you can do mean as 0, standard deviation of 1. But if you just want to get the x value directly, that's what we want to do, is get the x value directly, then you could just provide the mean that they gave you. So the mean is 240, and the standard deviation is 3. All right, so then and when we do that, what do we get? All right, so let's do that second. We could do vars and then go to an inverse norm, and we provide the area 0.95, and then the mean was 240, and the standard deviation was 3. Okay, so we got 244.93. Okay, so we got 244.93. If you calculate it like this, if you calculated this the way we did here, let's see what we got. 240 plus 1.64 times 3. Yeah, you get a pretty similar result, 244.92. All right, so 244.93. So that's going to round. The closest value to that is, looks like it's D. Okay, all right, now remember that we got, the answer was 244, which means that that's probably one of the least values. But that means that you could get something like 245 or 246. Okay, so that's the closest one. That's the best answer. All right, so number 15. Cheryl practices hitting a softball in an indoor stadium by using both an aluminum bat and a composite bat made of carbon fiber and graphite. She records the distance traveled by the ball for each hit. Let X bar 1 represent the average distance traveled by balls hit with the aluminum bat and X bar 2 for the composite. Cheryl's batting practices hits are independent. Which of the following conditions are sufficient to model the sampling distribution of X bar 1 minus X bar 2 with a normal distribution? All right, so let's look at the conditions. The conditions to be able to approximate this with normal is that the N1 has to be greater than or equal to 30, and N2 has to be greater than or equal to 30. Okay, so the sample size for the one bat has to be greater than 30, greater than or equal to, and then the sample size for the other bat has to be at least 30. Okay, for us to be able to use the normal distribution for X bar 1 minus X bar 2. So there has to be at least 30 recorded distances for each type of bat. Now the distribution of distance traveled by the ball is approximately normal for each bat. That's another condition too. So like if we know that the distribution is approximately normal for the bat, then for each bat, so for example, if X bar 1 is normal and X bar 2 is normal, or if X1 is normal, sorry. If X1 is normal and X2 is normal, then that would work as well, okay? So then that's sufficient enough to model it, okay? So either you can have 30 recorded distances, or you know that the bats are normal, right? Like the distribution of distances traveled by the bat. The total number of distances traveled is at least 60 for the two bats combined. No, that's not correct. It can't be. You can't just do 30 plus 30 is 60, because you don't want the two bats combined, right? So you don't want to combine the two bats. You just want them individually and independent. Individually, they have to be greater than or equal to 30. Okay, so the answer is D. All right, so let's look at the free response questions. So the U.S. Census Bureau collects information from every household in the United States, including household income. One value of interest is the interquartile range, or IQR, which gives the spread of the middle 50% of the household incomes. A random sample of 200 U.S. households is selected, and the IQR of the sample is recorded. This process is repeated 100 times, and a dot plot of the results is provided. What does the dot at 80,000 represent? Okay, so let's look at the dot at 80,000. So that's this dot right here, that little dot there. So remember, this is the sample IQR. So they took a sample of 200 households, and then they calculated the IQR from that sample. Okay, so what does this represent? This represents one random sample of 200 U.S. households with a sample IQR of $80,000 calculated. For that sample. Okay, so part B, the true IQR for the population of U.S. households is $64,000. Based on the dot plot, does the sample IQR appear to be an unbiased estimator, and explain? Okay, so remember that for something to be an unbiased estimator, the mean of that estimator, we'll just say estimator, has to be equal to the true mean, the true value of the population. Okay, so let me just write the population value. Okay, in this case, the population value is the IQR. So we're saying that the mean of the IQ of the sample IQR, so we'll say IQR S for sample, is equal to the IQR of the population. Okay, we'll say P for population. All right, so that's what makes it an unbiased estimator. Well, is that true here? Well, they said $64,000 was a true value. Okay, so 64,000 is around, well, this is 62 and a half, so 64 is like around, maybe around here, right? That's the true value. But if you look at that, 64,000, it's gonna be like around here. But if you look at it, it does appear that like half of the curve is there and half of the curve is there. That does appear to be approximately the average of this distribution right here. So if I look at this distribution, that does appear to be the average of that. Or it's pretty close to it. Okay, so in that case, if it's close to it, then we can see it does appear to be an unbiased estimator, right? So we're going to say yes, it appears since the true IQR value is close to the center of the sampling distribution. Of IQR, right? Oh, I should say the sampling distribution of sample IQRs, right? We can say roughly half is to the left of $64,000 and half of data to the right. Okay, so looking at this distribution, we see about half is to the right, about half is to the left, which is characteristic of that, that being the center right there, all right, which is close to the 64,000. All right, so that takes care of number 11. So number 11 is just about unbiased estimators and definition of that and what it means to be an unbiased estimator. Number 12, in the US, about 13.1% of people are left-handed. Suppose we take a random sample of 80 people in the United States. Okay, so we got N is 80, and we got 13.1%, so that's the population value, 0.131. Calculate the sample proportion who are left-handed, or p hat. What is the shape of the sampling distribution of p hat? And justify. Okay, so remember, to determine whether it's normal or whatever, we have to, it has to satisfy the conditions, right? So it has to satisfy the large counts condition. All right, so NP is equal to, so here we got 80 people times 0.131. So in that case, that's 10.48, which is greater than or equal to 10, so that's good. And then let's do N times 1 minus P. So 80 times 1 minus 0.131, which is 69.52, which is greater than or equal to 10. So it satisfies the large counts condition. And since it satisfies large counts conditions, that means it's approximately normal. Okay, so now what are the mean and standard deviation of the sampling distribution? Okay, so then the mean of the sampling distribution of p hat, according to your formula sheet, is just p, the true value, which is 0.131. And then the standard deviation of p hat. Now remember, for us to be able to use this formula for the standard deviation of the sampling distribution, we have to assume the 10% condition. Okay, so is the population of 80 people in the United States less than 10% of the population? Yes. Okay, so let me put the 10% condition here. The sample of 80 is definitely less than 10% of the total population. So we can assume the 10% condition is satisfied, and then we can calculate the sigma p hat, right? So square root p times 1 minus p divided by n. All right, so then we got 0.131 times 1 minus 0.131 divided by 80. Okay, you calculate that, you get 0.0377. All All right, so those are my two things. Find the approximate probability that a random sample of 80 people in the US would have 8 or less people that are left-handed. Okay, so then in this case, it says find the approximate probability that random sample 80. So we got our sample size is 80, and then we have 8 or less people. Okay, so that means if it's 8 or less people, that means my p hat is, if we use 8, then it's going to be 8 out of 80 people, right? Which is 1/10 of the sample, which is 0.10. So we want the probability that p hat is less than or equal to 0.10, right? 8 or less. That's what they want. And we know that the mu and the sigma are, so we can just use normal CDF. We want 8 or less, so that means we're shading to the left. And this value is 0.10. That means my lower limit is -infinity, my upper limit is 0.10, but we can't just use -infinity, right? Of course. So we're going to use normal CDF. We get -1000 or -10 to the 9th power. Then we got 0.10. Then we get a value, the mean is, well, this is free response, so we're going to need to label our entries. So our lower is -10 to the 9th. Our upper is 0.10. Our mean is 0.103 or 131. And then our standard deviation is 0.0377. Okay, and let's see what we get for that. All right, so we got 0.2056 around there by using normal CDF. Okay, now, since this is a free response, on the AP exam, you can use the normal distribution to approximate it. If you use the binomial, if you use the binomial distribution, so technically you can use the binomial distribution here, then you would get about 0.26, okay, 0.26 something if you did the binomial distribution. But again, I think it was pretty the way the question led you. It led you to say, okay, what's the shape is normal. So then you can, it led you to the conclusion that you can use normal CDF, right? But if you decided to use binomial, you would still be correct. You just have to make sure that you do it correctly. You get 0.2637. All right, so part D, what would happen to the shape, center, and variability if the sample size were 50 instead of 80? Okay, so what would happen to the shape and center variability if the sample were 50? Okay, so if it was 50, then when we do this, 50 times 0.131, that would not, that would actually fail this test. It would not be greater than or equal to 10, right? And then therefore it would not be approximately normal. Now, what shape would it be if it's not approximately normal? Well, because if this is value of 0.5, because P is 0.131, that means most of the data is going to go here. And so then it's going to end up being skewed to the right, okay? If P were like 0.7, then most of the data would be here, and then it would be skewed to the left, right? Can you see that? But if there's a balance between the P and then the sample size, then it's going to shift it and make it normal. But here, since the sample size is too small, it's going to make it skewed right. All right, so since P is 0.131, which is less than 0.5, then the shape is skewed right. All right, and then the center would stay. The center would still be the same. The center wouldn't change because if it's skewed right, I mean the center is still going to be whatever the center is. because of the formula, right? Because the formula is still the same. The mu p hat is still going to be p, irregardless of whether it's, you know, skewed left, skewed right, or whatever. It's still going to be equal to p. Yeah, so yeah, this would be the same as p, as long as p hat is an unbiased estimator, which it is. We know that p hat is an unbiased estimator, so we know that that's going to be true. So the center is not going to change. So the center does not change since mu p hat is equal to p. And then, so we talked about the shape, we talked about the center, and then the variability. The variability is going to change though, right? So the variability would increase because remember that the formula for the variability is that. So if this number is smaller, that means that the variability is going to be bigger, okay? Would increase. Since sample size is smaller. All right. All right, so let's look at number 13. Trey has a serious hobby of solving the 2x2 Rubik's Cube. He is preparing for a speed cubing competition and keeps track of his solve times. His solve times are approximately normally distributed, okay? And with a mean of 5.39 seconds and standard deviation 1.07 seconds. What is the probability that one of his randomly selected solve times is less than 4 seconds? Okay, so one of his randomly selected solve times, that's x. So if x is the solve time, then they're talking about x. They're not talking about x bar. So the probability that x is less than 4 seconds. So we're going to use normal CDF. It's normally distributed, and we're looking at 4 or less than 4 seconds. So that means that the left lower value is negative infinity. The upper value is 4, right? So it's from there to there. So we're going to use normal CDF and negative big number. So negative 1,000 or negative 1 trillion. That's what I'm going to do here. And or rather negative 1 billion. Sorry, I said trillion. Negative 1 billion, 9 zeros. And then whatever number you want, big, negative, and then we can do, what was the upper? It's 4. So upper is 4, and then our mean. And again, I gotta show my limits. I gotta show my work here because it's a free response here. So the lower is negative big number, so negative billion, and then 4. Upper value is 4. And then we have our mean is 5.39 seconds, and then our standard deviation is 1.07 seconds. All right, and we do this, we get 0.09696 for the probability. All right, so in the competition, speed cubers are ranked by their average of 3 solve times. By the average of the 3 solve times. What is the probability that a random sample of 3 solve times, okay, so n is 3 here, and then it's a random sample, would have a mean, so x bar. So they want the probability that x bar is less than 4 seconds, okay? So remember that the mean of x bar is the same thing as the mean of the original, which is going to be 5.39, so that's not going to change. However, the sigma x bar is going to be sigma over square root of n. The sigma was 1.07, but then we got to divide that by the square root of 3. Okay, so let's do that real quick. 1.07 divided by square root of 3, 0.618. Okay, so 0.618. Let's do that again. 0.618, yep. 0.618. And then we can use the normal CDF. Okay, so we got normal CDF. We want it to be less than 4. So again, it's the same, similar. It's negative, lower equals negative 10 to the 9th. Upper is 4 still. The mean is 5.39. And the standard deviation is 0.618. And we'll just put the answer here. So we'll do that there, and we get approximately 0.0122, around there. Okay. All right, so let's do part C. Was the probability for part B less than or greater than probability for part A? So obviously we can compare the answers, and we can say probability for part A was less than part B because means are less variable than individual values. Individual values tend to vary more. Averages tend to vary less, okay? Are less variable than individual values. I.e., because remember, the mean, the sigma x bar was over square root of n, okay? So, which makes it less likely to get a value at a certain distance away. At a certain distance or further from the mean. Okay. All right, so if you mention something like, the sigma x bar is less than the sigma, and then that influences the probability, so, something like that. All right, so number 14, trace solve times. So this is the same thing. Actually, here, they actually changed up the mean and standard deviation here, so we got to be careful with that, okay? So Trey was the same. I think Trey was the same. Let me see. Yeah. But now this time we are comparing Lunaria's solve times are 6.42 and 2.31. Okay, so we got here mu 1, sigma 1, but then we got mu 2, sigma 2. All right. Cubers are ranked by calculating the average of 3 solves. Suppose that we take a random sample of 3 of Trey's and then select a separate random sample of 3 of Lunaria's solve times and calculate the mean x bar 2. Then we're going to subtract them. So x bar 1 minus x bar 2. Give the following. So what's the shape going to look like? All right, so the shape is approximately normal. Since x1 and x2 are both approximately normal. Okay, because they told you that they were both approximately normal. Okay, the center is going to be the mean of x bar 1 minus x bar 2. According to the formula sheet, is the mean mean of 1 minus mean 2. So mean of x1 minus mean of x2. Okay, which in this case, if you look at the means, it was Trey's time minus Lunaria's time, 6.42, which is negative 1.03 seconds. And then we'll do the variability, so that's mean x bar 1 minus x bar 2, and then there's a formula for that, which the formula is the square root of sigma squared 1 over n1 plus sigma squared 2 over n2. So that's the formula from your formula sheet. So we can check that just to kind of show you. So let's check that out real quick. All right, so let's go back to that formula sheet so we can kind of show you where to find it. All right, there you go. So there's mu1, mu2, and then sigma squared 1, sigma squared 2, right? That's what I was trying to show you earlier. All right, let's go back to that problem. so we got square root, and if we go to trays, it says trays standard deviation 1.07, and then the other one is 2.31. So 1.07 squared divided by 3, 2.01 squared divided by 3. Okay, so we calculate the variability, and that's going to be about 1.47 seconds. All right, so part B, what is the probability that Trey's mean solve time is faster than Lunaria's solve time? So the probability that x bar 1 minus x bar 2. Now, if Trey is faster, that means when we subtract them, it's going to be, well, if Trey is faster, that means the x bar 1 is smaller, right? So x bar 1 smaller, meaning he's faster. Smaller time means faster, right? So that means that this is going to be negative. So x bar 1 minus x bar 2 has to be less than 0. That's what they're looking for. And so, okay, so then in that case, we're doing the area to the left. So we have negative infinity up until the value of x bar 1 minus x bar 2, which is the negative 1.03. Because that's what we calculated over here, recall. All right, so we got normal CDF of negative billion. Then we got negative 1.03 for, we got to show in order to get full credit on the AP exam, be sure to label your stuff, okay, if you're using the calculator speak. So negative 10 to the 9th. Upper is negative 1.03. The mean is equal to, I'm sorry, we want the upper to not be negative 1.03. We want the upper to be 0. I'm sorry about that. Less than 0. We want it to be less than 0. The mean is negative 1.03 because that's what we got there for the mean. And then the standard deviation is going to be 1.47 because that's what we got earlier. Okay, and we calculate it. So when we calculate it, we should get about 0.7580. All right, that's going to do it for the video, guys. Hope you found this useful and informative. And as usual, I'll see you in the next one.